Preparation of natural rubber for producing tires. First is the harvest. The latex is harvested by affixing a container to the rubber tree, which is referred to as tapping. Upon tapping of the rubber tree, the white colloidal fluid of latex exudes from the tree bark, and a series of biochemical reactions are triggered that change the component and colloidal stability of the latex. Coagulation process occurs as latex is exposed to air. This is due to the bacteria in latex that produce acid. Acid accelerates the coagulation process, while alkaline prevent the coagulation of latex, such as ammonia. Ammonia will neutralize the acid produced by bacteria, thus prevent the coagulation. So this coagulation step is necessary to cheese the flow of latex and plug the wound of the tree as a natural defense mechanism of the plant against the pathogen. So there are two stages of phenomenon when coagulation of latex takes place. So the first stage involves the destabilization of colloidal suspension of latex to enhance the particle collision, and the second stage is the aggregation of the natural rubber particles, leading to the formation of coagulum, known as coagulation. H plus ion in the acid will neutralize the negative charge particle membrane, thus elimination of repulsive force between the particles. Finally, adhesion and collision between the rubber particles take place, which break the membrane of the rubber particles. So all of the molecule of rubber is released and clumped together, forming the latex coagulates. Sheet formation is the process of rolling and pressing to remove the excess water. The sheet is known as scrape. Rubber was washed to remove impurity and dried. It was hung over racks in smokehouse or left out to air dry. It is to improve the quality and purity of the rubber. Mastication or compounding and mazing stage 1. Mastication is the mechanical process involving kneading, rolling, or shearing the rubber to break down the polymer chain and improve the plasticity. This process uses mills or extruder. Heat is generated to help soften the rubber to be more workable. The rubber is compounded with various additives such as carbon black for reinforcement, antioxidant, accelerators, and fillers. Fillers example are China clay, polymer, recycled rubber, and pigment. Additives enhance the specific properties of rubber, such as abrasion resistance, flexibility, and wear resistance. So this mastification shortens the molecular change, thus reduce the molecular weight and viscosity. Vulcanization is the cross-linking polymer chain of rubber with sulfur or other vulcanizing agent to improve the mechanical properties of rubber, such as elasticity, strength, and durability. So heat treatment phase occurs at elevated temperature in presence of vulcanizing agent and accelerator. So rubber is cooked to create extra bond or cross-link between the molecules so that they don't easily fall apart. So in result, the rubber is harder and durable. Rubber that has fewer cross connection between its polymer is softer. The elasticity of the rubber is reduced as the number of cross connections increases, resulting in harder rubber. Rubber would be sticky when hot and brittle when cool if it wasn't vulcanized. The rubber then will mix with vulcanizing agent. The shape of the rubber is cured in a mold under heat and pressure to achieve the final shape and properties. Curing further cross-link the polymer chain. The shaping method of curing is the extrusion, calendering, molding, coating, and casting to make it more stable and durable rubber product. Lastly is the quality control. This is to ensure the rubber product meets the desired specification. This includes testing for physical properties, chemical composition, performance characteristics. The main chemical present in natural rubber is polyisoprene. Instrument and tools to identify the polyisoprene is the infrared spectroscopy (IR), thermal analysis technique, nuclear magnetic resonance NMR spectroscopy, mass spectrometry, gel permeation chromatography, and X-ray diffraction. Polyisoprene is a polymer composed of repeating isoprene monomer units. Isoprene, also known as 2-methyl-1,3-butadiene, has the chemical formula of C5H8. Polyisoprene can exist in both cis and trans configuration, with the cis configuration being the most common in natural rubber. In natural rubber, the polymer chains are predominantly in the cis-1,4 configuration. Properties of polyisoprene is flexibility, resilience, elasticity, tensile strength, low temperature flexibility, abrasion resistant, electrical insulator, chemical resistant, and biocompatibility. The application of polyisoprene is rubber production, latex product, adhesive, bottle, elastic band, footwear, medical devices, textile coating, and sports equipment.
There are 5 industrial production methods. First is Cumin process. Isopropyl benzene oxidized in the air to produce phenol and acetone. Acetone and phenol are produced at the end of the reaction. Second is from alkanitriles. Ketones are created when the Grignard reagent reacts with alkanitril and is then hydrolyzed. Thus, ethanitrile and methyl magnesium bromide react, and hydrolysis occurs, then acetone produced. Third is hydrolysis of gem dihalite. Gem dihalite undergo alkaline hydrolysis to yield ketone. Non-terminal carbon atom is joined to the 2 halogen atom. Thus, 2,2-dichloropropane will be produced, and it will undergo alkaline hydrolysis again to produce acetone. Fourth is oxidation of isopropyl alcohol. 2-propanol undergoes an oxidation process to yield acetone. Last is ozonolysis of alkenes. An ozonide is created when ozone is passed through an alkene in an inert solvent. Compounds called ozonide are explosive. Depending on the structure of the alkene, it will then warm up with zinc and water to create aldehyde, ketones, or an aldehyde and ketone. Thus, acetone and acetaldehyde are produced by the ozonolysis process of 2-methyl-2-butene. Chemical mechanism production of acetone. The first is alkylation. In the presence of an acid catalyst, benzene and propylene react to generate a carbocation intermediate. Cumin is created when the carbocation breaks the double bond in propylene. Then in cumin oxidation, the presence of a metal catalyst, cumin combines with oxygen to produce cumin hydroperoxide. The last step is hydrolysis, when acid hydrolysis of cumin hydroperoxide breaks the oxygen-oxygen bond and produces phenol and acetone. This is the chemical reaction of cumin process, where the conversion of benzene and propylene into acetone and phenol with the cumin acting as an intermediate compound.
Ethylene hydration is a chemical process in which ethylene gas C2H4 reacts with water H2O to produce ethanol C2H5OH. The reaction is typically catalyzed by an acidic catalyst such as phosphoric acid or sulfuric acid. The process of ethylene hydration is typically carried out under high temperature and pressure conditions to favor the formation of ethanol. First is adsorption. Ethylene molecules are adsorbed onto the surface of catalyst. Catalyst diatomaceous earth will support phosphoric acid. Surface of diatomaceous earth is coated with phosphoric acid so that it acts as acid catalyst. Concentration of phosphoric acid is around 85 until 19%. Second is the activation, which is formation of carbocation, and hydration. Water molecules react with activated ethylene species to form the ethanol molecule. Water is vaporized and added to vapor of ethylene at pressure of 65 until 70 atm and heated to temperature of 300 degrees Celsius. The reactant mixer is fed to reaction tower from top. Catalyst solution of phosphoric acid also fed to top of the tower as makeup when required only. The impurity present in ethylene mainly is acetylene. This will also participate and react to produce acetaldehyde by reaction. Lastly is the desorption. Ethanol molecule dissolve from the catalyst surface and regenerating active site for further reaction. So this is the deprotonation to form the alcohol. The product mixture containing alcohol, unreacted ethylene, water, and acetaldehyde are sent to separator. Ethylene and water are separated from bottom, and unreacted ethylene removed from top and scrubbed with caustic soda to remove trace of acid. A high-pressure stripper separates acetaldehyde and sends it to hydrogenator to produce ethanol with the help of nickel catalyst. Ethanol or ethyl alcohol is a chemical that is volatile, colorless, and flammable. It can be produced from petroleum via the chemical transformation of ethylene, but it can also be produced by fermentation of glucose using yeast and the other microorganisms. The current full ethanol plants make ethanol via fermentation. For fermentation, yeast is needed. The other enzymes are used, but yeast is the most common. A sugar, such as glucose, is the carbon source, and the anaerobic condition without oxygen must be present. First is milling. Whole corn kernels are ground into a form of flour or meal. The meal is mainly starch. A starch is a carbohydrate made up of long chain of sugar and molecules. Second is liquefaction. Water is added to the meal to make a slurry. The slurry is heated to break the long starch molecule into smaller pieces. The enzyme alpha amylase is added to catalyze the breakdown of starch. Next is saccharification. Starch molecule pieces are broken down into simple sugar glucose. This reaction is catalyzed by an enzyme called the glucoamylase. Next is fermentation, where single-cell microorganisms, which is yeast, are added to the slurry. Fermentation is the biochemical process that occurs when yeast break down glucose. Yeast get energy from glucose, and then ethanol is produced. And then distillation and dehydration. The product of the fermentation process is only 10 until 15% ethanol. so it must be concentrated to become pure 100% ethanol. Lastly is denaturation, which is a small amount of gasoline is added to fuel ethanol to make it undrinkable. Application of urea is as fertilizer, feed supplement, chemical synthesis, automotive, cosmetic and personal care, de-icing agent and dental product. Application of butylene includes in polymer production, butyl rubber manufacturing, chemical intermediates, fuel additive, solvent and extractant, adhesive and sealant, and fuel and energy.
Preparation of cooking oil using palm oil. First is extraction. Once at the processing facility, the fruits are sterilized to eliminate bacteria and deactivate enzymes. Fruit is threshed to remove individual pieces from the bunch after sterilizing. Second is pressing. Crushing the fruit releases the oil-containing mesocarp in this process. After that, the fruit pulp and oil mixture is pressed to extract the oil from the solid. Third is clarification. This process involves heating the oil to break the emulsion and then centrifuging to separate the oil from the solids and water. Fourth is refining. Generally, degamming, naturalization, bleaching, and deodorization are steps in the refining process. Deodorization eliminates smells and odors. Degamming eliminates phospholipids. Neutralization eliminates free fatty acids. And bleaching eliminates colors and contaminants. Last is packaging. After that, the refined cooking oil is put into bottles, can, or other packaging for consumer distribution and purchase. One kind of nutrient that the diet can use as a concentrated source of energy is fat. Triglycerides, which are molecules made up of three fatty acid chains joined to a glycerol molecule, are the chemical building blocks of fat. Fatty acid is saturated and no double bond in bonding. Meanwhile, one kind of fat that doesn't solidify at room temperature is called oil. The sources mainly plants and the fatty acids are unsaturated. All have a double bond bonding. The difference characteristic between vegetable oil and animal fat based on tests. Vegetable oil is less intense than animal fat. Depending on the source of plant, they can have different tastes. For example, olive oil can taste fruity or peppery. Meanwhile, animal fat have a flavor that deeper and more pronounced, like tallow from cattle has a slightly meaty flavor. Based on stability, vegetables oils varies according on the type of fatty acid they contain and how they are processed. When exposed to heat, light, and air, oils high in unsaturated fat like olive and canola oil are more vulnerable to oxidation and rancidity. Higher saturated fat oils, including those found in coconut and palm oils, are more stable and appropriate for cooking at high temperatures. Meanwhile, for animal fat, when heated, it has a greater percentage of saturated fat, tend to more stable than vegetable oils. For instance, the high saturated fat content of lard and tallow allows them to be cooked at high temperatures without degrading or releasing toxic chemicals during frying. Meanwhile, for animal fat, it contains a larger percentage of saturated fat. So, cholesterol, which is exclusive to diet originating from animals, is also present in animal fat. However, certain minerals like iron and zinc, as well as fat-soluble vitamins like vitamin A and D, can be found in animal fat. This is the complete flowchart of crude palm oil. There are two types of refining, which are physical refining and chemical refining. Physical refining including the degamming, bleaching, and deodorizing process to produce two products which are refined, bleach, deodorized palm oil, and palm fatty acid distillate. The RBD palm oil just now will undergo fractionation to produce RBD palm oil and RBD palm stearin. As for the chemical refining, it will undergo alkali neutralization, bleaching, deodorizing, neutralized bleach palm oil, and fractionation to produce the RBD palm oil and RBD palm stearine. As for the measuring flowchart, oil, water, salt, and preservative, fat-soluble, and emulsifier are put into one mixing tank to mix all of this. Then it will goes to high pressure piston pump and then goes through SSHE tube cooler 1, 2, and 3 before it go to pin rotor. Again, will undergo high-speed pin rotor and double-stage homogenizer, then finally it will become a margarine.
Thank you.